And next up, we have a remote speaker, Alessandra Corsi from Johns Hopkins, who will be talking about following up on gravitational wave triggers from a radio telescope point of view. So, Alessandra, are you out there? Can you hear us? Can we hear you?
Can you hear me?
Yes, we can.
And do you see my slides?
Yep, we see your slides. You are good to go.
Perfect. Thank you very much for having me. Yes, so I'm gonna be continuing along the topic of multi-messenger follow-up, but I'm gonna be shifting the focus to radio wavelengths. Just a quick reminder, we had many awesome talks, but the motivation for going after radio emission from gravitational wave events is really simply sketched here. So after we have a compact binary merger, imagine this being the merger of two neutron stars signaled by the gravitational wave event. We want to really study, get the complete picture of the stuff, the material that is around that merger. So the gravitational waves allow us to see the compact region of space very close to what that merger remnant is, but electromagnetic emission gives us the view of what's around. And so in the optical wavelength talks, for example, that we've heard, in the case of binary neutron star mergers, you are sort of probing the neutron rich, roughly, isotropically distributed is a bit of a stretch here, but it's at large angles distributed around the merger site. What the radio wavelengths bring in is it is particularly able to trace emission coming from fast ejecta, so jets that are also launching these mergers. And where the emission is not thermal, it is synchrotron emission. And so you really want to pair radio observations with gravitational waves and optical observations in order to get the complete pictures of the various emission components that are around that merger event. So in my talk, I'm going to be speaking about ground-based gravitational wave detectors specifically. So those that can track gravitational wave emission from compact binary systems that involve neutron stars and black holes that have mass comparable to the mass of the sun. These are the current detectors, Virgo, LIGO, and Cagra, with 3 to 4 kilometers long arms. I will also project what the expectations might be for what we call the next generation of ground-based gravitational wave detectors, Cosmic Explorer concept and the Einstein telescope down here. Those are over the next decade, 2040s, you might think about, and they are envisioned as observatories that will have 10 times longer arms, and so 10 times the sensitivity of current ground-based gravitational wave detectors. So I'm going to be adding the radio into the picture, and I'm going to be adding into the picture what might happen into the next generation of observatories. This is, I'll go very quick on this, the sensitivity curves of these ground-based detectors. So on the y-axis is the strain. All you really care about is that the lower the noise, the lower this curve. And on the x-axis is the frequency ranges that these ground-based detectors are able to capture. If you notice, those are actually, when converted into sound, they're in the audible regime. But just as a reference, this light blue curve here is where we're at right now. And the next generation detectors, those with 40 kilometers long arm, would improve on that about a factor of 10 broadband. Okay. The other thing I wanted to bring into the picture is the fact that there are many facilities upcoming on various timescales that some of them we heard about that I could be talking about, but because of my particular bias, what I'm going to be focusing is gravitational waves that can be done in the, gravitational wave follow-up that can be done in the radio band, specifically using national US facilities. So this means that I do not own the facility. It's a shared facility. And in fact, the amount of time that we get allocated on those facilities is based on a competitive process. So this is like PI-driven science. In this image here, you see the 27 radio dishes of the Very Large Array. In front of it is the prototype antenna of the next generation very large array. So I'm not just going to be putting this in the context of next generation for ground-based gravitational wave detectors, but also for radio telescopes. And so the next generation very large array is thought to be a next generation interferometer where we can get 10 times basically the sensitivity of the very large array and VLBI level, sub-millisecond second level resolution. So I'm specifically looking into this, and the reason why I highlight it is because it brings additional challenges to what we've perhaps heard, and is the fact that the data have proprietary period, and then you can have multiple PIs, multiple users, potentially, right, targeting the same source in various different settings. Okay, so I mentioned that I'm mostly going to be focusing on the stellar, stellar mass, let me call it neutron star and black holes. So if you look about a scale here from lower to higher, masses of these exotic objects in the universe, neutron stars down here, and then all of the scale to the most massive black holes in the center of galaxies, my talk is really focusing on this very lower part. Where, again, this ground-based gravitational wave detectors are able to provide us triggers. So just to be fair, I'm leaving out a huge, chunk of the science. And so I'm calling multi-messenger here something very specific. Okay, so in the radio, what type of events you might expect? Well, first of all, is there's a golden one. So the GW17817 event we'll have heard a lot about, that this is the prototypical 1.4, almost 1.4 solar mass neutron star merger. The gravitational wave time frequency track is shown here. There was a gamma ray burst about 2 seconds after that. Purple here is the localization in the sky provided by ground-based gravitational wave detectors. It looks small, but it's not in terms of, typical localization areas. We heard in the previous talk about these bananas from LIGO and Virgo. And then the identification in the optical. Most of what you heard focused on the kilonova counterpart, so finding the optical counterpart. I am shifting in this talk, and I'm thinking of finding what is mostly synchrotron emission powered. So X-rays as shown here, that is the counterpart of GW17817, and that is the host galaxy. And then for that event, we saw the radio emission as well. So this, we call it is the golden standard because it's a binary neutron star, and we saw emission practically from gamma rays through the radio, so all of the electromagnetic spectrum. Specifically from the radio perspective, learning from GW17817, we can expect that there's going to be a big challenge in the radio, namely the fact that, as you see in this left-hand side panel, what we've learned by that multi-wavelength emission mapping of GW17817 is that the places from which the components from which you can get photons are different. There's a variety of possible emissions components. And so if that is the remnant compact object after this mashup of the two neutron stars, we said there's this cloud of neutron-rich debris that presumably power the kilonova. There's relativistic jets, that is what the radio is probing. And then there's potentially cocoons, so angular, wider angular distribution of ejecta that might reach, speeds at like 30% the speed of light. So you might still see radio from that. So this is a very quick overview just to say that when you go and look for radio emission from these fastest component in that messy ejecta, you have a lot of uncertainty in what both the luminosity, the radio luminosities, and the radio time scales that are relevant that you need to probe. So in this plot to the right, you see radio luminosity as a function of time and a variety of curves that basically fill in that plane. And these are representing the uncertainties that you could have. For example, that red area is a jet emission that could be seen either on axis, so very bright, or off axis, much dimmer. And potentially, if a neutron star survives after the merger, it can pump energy into the ejecta, so you can see brighter emission. And another component I can specifically point out is, for example, this disk wing component, which is not as fast as that jet, is maybe 30% the speed of light. And so you see it peaking at later times and at lower radioluminosities. So the variety of, ejecta speeds that you can have tell you that you can have orders of magnitudes scatter in luminosity and orders of magnitude difference in peak time scale. So this is not going to be, something easy, but it's something very promising from the perspective of wanting to understand the physics that goes around these mergers, and particularly that of the ejecta. This is the prototype case that I mentioned about, so the typical binary neutron star merger. It has been mentioned that lately we've had some excitement about potentially, new paradigms, and particularly the possibility of, looking at what happens in the case of subsolar neutron stars, so neutron stars that have masses much less smaller than the mass of our sun. It is a open theoretical question whether they can form. One of the proposed scenario has been that these very light neutron stars can form, in fact, in the disk of a collapsing massive star. And so there has been some excitement with a low confidence gravitational wave alert. S25018K is the phone number during the latest LIGO Virgo Kagra run. And just to say, we've carried out, a radio follow-up for that, detected a very faint counterpart, just focus on these 3 data points here. But you can see that involved in this case, looking at radioluminosities that peak, order 100 days after the event. So you really have to be patiently looking at that field, integrating as deep as you can. The other type of source that was mentioned in the previous talk is potentially binary black holes. Here I'm mentioning a slightly different scenario where you might imagine the stellar mass binary black holes having some fossil disks around them. In principle, you would expect them to be clean and not give off electromagnetic emission. But it has been proposed in several models that if there is basically a bit of disk material remaining, you could have accretion of that reactivated after the merger, and so potentially launched of relativistic jets. Now, why are we talking about this? This is a, so it seems like a very low probability thing to happen. But the reason why this has, gained interest is particularly indicated in this right-hand side plot. So you can ask yourself, if you look at all of the binary black hole mergers in terms of chirp mass, take it as a measure of how heavy they are in combined mass. If you look at all of the ones that have been detected so far, for how many of them has there been a claim that something like, a jet, and particularly a gamma ray emitting jet, could possibly be there. So you go and look at the potential association with gamma ray triggers, and the colored ones here represent some of the events for which, a low confidence, but still there, potential association has been claimed. They're very low confidence, but the intriguing part is perhaps that you have one at least of those associations per run of the ground-based gravitational wave detectors. So I share the idea that, okay, this is a low probability, scenario, but it's definitely something that I don't want to forget about. I want to go look and see if there is potential for that. I won't go into the details of the lower plot here, but this is just to show you that in terms of doing radio follow-up, what you're constraining is the potential existence of that jet. And so you can constrain how energetic it is and how dense the interstellar medium around it is, even if you have known detections. So in this plane here, you see the exclusion regions from the radio and from the gamma rays to the left. Okay, so hoping that I have motivated enough for the radio follow-up, I'm going to shift towards the questions that were asked. So what are the challenges? Well, I think Mark Lacey after me is going to talk a bit much more in detail about this, and he's way more expert. But the big challenge I have every day when I'm trying to reduce these data sets is the fact that in general, these are demanding in terms of the processing that needs to happen to go from the from the raw data to the images. And so the key point is that for radio interferometers, we don't image directly, but we're sampling the sky's Fourier transform, and so we need to go from visibility into forming an image. Without going into the details, this has two major processes: a cycle where you're basically gridding and doing the FFTs, and a cycle where you're just more, it is in generally faster, where you're working in the image domain. But this overall poses some challenges in terms of file input and output and memory, which are hard to tackle if, for example, you're trying to reduce an order of 150 gigabyte for one observation on a laptop. And so typically what we do right now is we use the computing resources offered by the National Radio Astronomy Observatory. But even there, the input-output is, file input-output is demanding in the sense that you would ideally have to match that to the size, that and the memory, to the size of your data sets. And these are big data sets. So that is definitely something that introduces substantial latency. Just to give you an idea, lately some of the images we've collected took like for one observation, like order from a few days to a week to reduce. And then you're observing these things, for up to 100 days. So you're doing many iterations of this. The other thing I wanted to point out is a guess estimate that I was working out for myself, just to understand, okay, now let's think about next generation and how all this is going to scale. And so while we're not, these data, because of how rare these events are not really heavy today. I mean, for the latest event that I mentioned, the subsolar candidate, we collected about 2 terabytes of data. For GW170817, the golden candidate, across multiple years, we have about 8 terabytes of data. So these are small data sets. And for the next observing round, the so-called IR1, probably based on our program, it's going to be something like 10 terabytes. But when you start scaling these things up for next generation detectors, things become really interesting, especially if you want to build, if you think about, building an archive with all of the multi-messenger observations, specifically for radio facilities. And so doing that exercise, we're going to see, as you can see from this plot here, a huge increase with 40 kilometers long ground-based detectors in the number of binary neutron star mergers that we expect to detect, even if you select the very special ones with awesome localization, so within 10 square degrees in the sky. And if you assume that for these, 1,000 BNSs over a run of 3 years, you do the same type of follow-up that you've been doing with GW170817, but with a facility like the NGVLA, so where the data rates are going to be much higher, you could easily push this from a terabyte today to, exabyte tomorrow. This obviously assumes that you want to keep all of the raw data. The science-ready data products are 1,000 times lighter. But I think there's a potentially, a nice, interesting challenge on the horizon. Again, this depends on whether we're going to have these next generation ground-based facilities. I think we should be thinking, beyond the problems we have today, but the ones that we might have in 10 years or so. There's a potential for also optimizing all this in terms of lags. I mentioned that, it can take a while to follow the whole event. You need to keep monitoring potentially for years after it. And so lately, we've also been thinking about, okay, how can we orchestrate this whole process in a bit more, efficient way. So we're also working on, this is a paper we recently published on, using perhaps AI-driven techniques to streamline some of the things that human beings currently do as we are listening to the gravitational wave alerts, responding and taking radio data, and then trying to share that data, trying to share the results of the various modeling across observers that might have data they're not actually sharing among themselves. As I mentioned, the National Radio Astronomy facilities are PI-driven, and proprietary periods are, different, might be different, and the users are different. So there's also more of a sociological aspect of this that is interesting. But anyway, in the interest of time, I'll end here and I'll take questions. Thank you.
All right, thank you.